Hello everyone, I'm Miao Huazhang from Several Datasets 1 in Australia. Today at the WVAQ workshop at WACV 2026, I will present our work, Quality-Driven and Diversity-Aware Sample Expansion for Robust Marine Obstacle Segmentation. This work targets a key challenge in the autonomous maritime navigation. Robust segmentation when diverse and high-quality training data is scarce and expensive to label. To address this, we propose an inference-time data expansion pipeline that generates high-quality, diverse samples without retraining the diffusion model, improving the robustness in real-world dynamic conditions. First, I want to highlight the core challenges: data scarcity in marine computer vision. Marine scenes are very difficult for the autonomous surface vessels. You often have sun glittering, fog and haze, and consistently changing wave patterns. So model trained on clean and limited data tend to fail under these conditions. The bottleneck is twofold. First, public datasets are too small and often structurally repetitive. For example, the same water horizon sky layout again and again. Second, pixel level annotation is extremely expensive. As a result, we end up with models that look good in distribution, but struggle to generalize to unpredictable open sea conditions. To address this data scarcity problem, we built a generation pipeline with two parts, a training stage and an inference stage. In the training stage, we follow the existing ControlNet++ setup to learn a layout consistent generation. Then in the inference stage, we introduce our main contribution, a two-stage inference strategy that improves diversity without retraining the diffusion model. Specifically, we added two modules, a class-aware style bank, which constructs the richer, high-entropy prompts while staying grounded in the class present in the mask, and an adaptive annealing sampling, which dynamically balances the visual diversity and layout fidelity during the sampling using a feedback controller. Now let's first talk about the class-aware style bank in more details. In marine obstacle segmentation, the label space is very small, typically just sky, water, and obstacle. If we rely on simply class-list prompts, the diffusion model often falls into model collapse, where many generated images look almost the same. Our style bank addresses this by abandoning each class into rich set of realistic style descriptors. For example, class-aware descriptor could provide different patterns of obstacle, wave, or cloud, like the water could become choppy harbor waves or the glittering calm surface. We then combine this class-level descriptor with global scene pattern, like the foggy dawn or the harsh sunlight. The result is high-entropy prompts that stay semantically grounded but produce much more visual variety. The second component is the adaptive annealing sampling. The key issue with the standard diffusion sampling is that the conditioning can be too rigid, so the model keeps producing very similar textures and appearances. So what we do instead is to introduce a dynamic trade-off between the exploration and alignment, as illustrated by the two curves on this slide. At the early sampling step, we loosen the conditioning and apply stronger perturbations, so the model can explore more diverse visual effects. Then, as we move to the later steps, we gradually tighten the condition to bring the generation back into the strict alignment with the input mask. What makes it adaptive is the feedback controller in the middle. We monitor a layout consistency signal during the sampling and use it to adjust how strong we are annealing, so we get more diverse but still preserve the precise segmentation boundaries needed for segmentation. We evaluate our framework across three major backbones: deep dive variance tree, mass-to-former, and SAM adapter. Across all models, our method is consistently competitive on F1 score, and it reduces the false positive with strong precision, while keeping lower water edge RMC. Overall, it gives a cleaner and more reliable obstacle detection than the baseline method. Here is a visual comparison of a different method. Our method generates synthetic samples that are visually realistic and diverse, while staying strictly aligned with the input mask layout. As a result, model trained with our data produce cleaner and more complete obstacle segmentation with fewer false alarms, even under challenging conditions like the fog and water reflections. In conclusion, we presented a plug-and-play strategy for robust marine perception that balances diversity and fidelity. Thank you for your attention. If you are interested in more details, please scan the QR code to visit our project page or reach out to the authors via the email here. We are happy to answer any questions. Thank you very much.